Hello. In this video, we will discuss about domain of functions. I'll give you examples and we'll see how to write domain of functions. I won't really write range of these functions. It is an exercise for you to do it. So do it on your own. How to write range. Okay, it's very similar to the domain with maybe some more restrictions. Okay, so in general, if a function is given to you and no conditions are given, then what do we assume? What is a domain? In that case, domain is set of real numbers, right? How do we write this domain? In general, we write it like this. D for domain, X for the independent variable, and belongs to a set of, X belongs to a set of real numbers. So this is epsilon, which means belongs to. This is the independent variable X, which represents the domain for us. All permitted values for independent variable X in the function is the domain, correct? And normally it is set of real numbers. We will use number line to represent domain in couple of cases. We'll also use, as discussed earlier, set notations, interval form, and set builder form. Number line. Let's have a look at the number line. Normally we just show a number line like this, writing 0 here, showing that it extends to both the sides, positive and negative. It approaches positive infinity, negative infinity, and all the numbers in between. Now I will also sketch some diagrams for different kind of functions, but really will not put them on a coordinate system. Imagine that we have a coordinate system here, okay? That is, we have a number line which represents the x-axis and the y-axis is here. Since my concentration today is only on domain, I will not plot my graphs on a coordinate system. Okay, I'll just plot them in general, not mentioning about the y-axis at all. Okay, it makes sense because let's say if we have a function here, okay, then I'm not really interested in the y values. I'm interested whether it is continuous or not along the x-axis. Now, if it is continuous all along the x-axis, then we say that the domain is set of real numbers. But if it is discontinuous somewhere, then we say that there are restrictions to our domain, and domain cannot be those values where it is discontinuous. Okay, so let's move forward and take some examples. To start with, let me take examples of functions where the domain is continuous. Now, some of the good examples are straight line, represented by the function y equals to mx plus b. As you know, these straight lines could be lines like this with slope positive, or lines like this, slope negative, or even a horizontal line. Is that right? In all the three cases, you can say if I draw a line here, right, in any direction, they all are continuous, right? There is no discontinuity involved. They extend from minus infinity to plus infinity, and therefore the domain of these lines is a set of real numbers. X belongs to R, correct? Now let's take some more examples. For example, if I write y equals to ax square plus bx plus c, what does that represent? You know, it's a quadratic function, right? Now, quadratic function is also continuous all along its domain. The only thing is the parabola could be going up, right? Or it could be going down. So in its domain, it extends from minus infinity to plus infinity. Correct? We are not really bothering the turning point. Turning point will give you restrict the range. It has a restricted range, correct? Okay, if I draw it here on the axis, for example, if I draw it like this, right? And if this point is, let's say, 4, it touches 4. In that case, yes, domain is all real numbers, correct? Range could be restricted. Here, the range is what? range is greater than equal to 4. Is it okay? So that's the restriction on range which you should be in a position to write by now. Okay. Now let's move on to more higher degree polynomials. For example, if I write a function like an x to the power of n plus an minus 1 x to the power of n minus 1, so on, a2 x squared. What does this equation represents? It's a polynomial, right? Now, in this polynomial, it could be of degree 3, 4, 5, whatever. But, the degree could be odd or even, right? If the degree is odd, in that case, the polynomial will look something like this for an odd degree polynomial, right? This is odd degree polynomials. Well, it could face different direction also. If the coefficient is positive, this side will go up and this will be down, correct? But in case, let me write if n is odd. But if and a is positive, okay? A is greater than 0. In that case, it will be like this. But if n is odd and a is less than 0, in that case, our graph will be reversed, right? It will flip. So here, it will do something like this. But in both the cases, as you can see, the domain is set of all the real numbers. Correct? Now, let's take a scenario where n is not odd but even. Okay? In case n is even, what happens? And a is greater than 0. In that case, it will face up, right? Something like this. Well, the range could be restricted, but the domain is set of all the real numbers. I hope you appreciate that part, right? I don't really have to draw the coordinate system to show you the graph, right? So we'll take another example where n is even and a is less than 0, okay? In that case, how the graph will look like? Somewhere like this, right? Of course, the graph extends from minus infinity to plus infinity, correct? Now, by now, I think you can appreciate that I really don't have to represent my graph on a coordinate system to show you the domain of the function, right? So that's how it is. All these functions are continuous, and many more are continuous. For example, y equals to absolute x. Now, y equals to absolute x will be a function like this, right? Now this function can be transformed, and howsoever you transform this function, you may do it like this in general, right? Or like this, correct? Wherever on the coordinate system. You will notice that it is a continuous function and the domain is set of real numbers, correct? So all these functions are the functions where the domain is set of real numbers. Now we'll move on to some more functions where the domain could be restricted. Okay, and let's see if the domain is restricted, how to represent it and how to write it. Okay, for the first function, let's take the square root function. Now, if I say y equals to square root of x, well, y equals to square root of x could be drawn like this, right? Here, the domain is restricted. How? The domain is set of real numbers greater than 0. Why? Because in the radical, you cannot have negative value. If in the radical you have a negative value, then the answer does not belong to set of real numbers. It becomes a complex number, correct? So here the domain is x belongs to real numbers where x is greater than equal to 0. Okay? So in this, we can represent it in interval notation also. And there we will write because it includes 0, we'll start with this and we'll say 0 and it goes up to infinity, where infinity is not included. Is that okay? So we could write this radical or square root function in this form. Here's a 0 and there it extends to plus infinity. Now we can have a transformed square root function. So for example, we have square root of 3x minus 6. Now how to find where is the restriction now? The simplest way to do it is to equate the portion inside the radical to greater than or equal to 0. Correct? So we'll do our maths here. We'll say 3x minus 6 should be greater than or equal to 0, and we'll solve this inequality. 3x is greater than or equal to 6, or x is greater than or equal to divided by 3, 2. So here we can write that domain is set of real numbers where x is greater than or equal to 2. Correct? And on a transformed function like this, you will see basically x is greater than 2. It moves 2 units to the right. Right? Why 2 units? Well, let me show you that part also. When we say y equals to, we'll take 3 common, x minus 2. Okay. So this is the 2 which shows that our function moves 2 units to the right from the origin, right? And that's how it is. So a radical function, rather a square root function, has a restriction, and because in the radical, in the square root, it should always be positive. So we can equate it as an inequality, that all this should be greater than equal to 0, and then get our answer. Fine. Now let's look into reciprocal function. Reciprocal function is of the form y equals to 1 over x. As you know, reciprocal function can be drawn like this. So it is never 0, right? Because 1 over 0 is undefined. 1 over 0 is undefined. As the function approaches 0, you can see if we are approaching from the negative side, as the function is approaching 0, the value increases unbound. It approaches minus infinity. As you approach 0 from the positive side, the value increases unbound to positive infinity. So it never reaches a particular value. We say at 0, the function is undefined. So a reciprocal function has a domain with restrictions, okay? And this domain we can write as x belongs to real numbers where x is not equal to 0, okay? So this is a better way, because there's only one value which is not in the domain. Rest all belongs to the domain. So this is a good way of writing your domain, okay? So here we'll write domain dx equals to this. Now let's consider a few transformed functions of y equals to 1 over x. We can write this as 1 over 2x plus 3, for example. To find the domain, you have to equate that your denominator, which is 2x plus 3, it should not be equal to 0. Is that okay? Because 1 over 0 is not defined. We'll solve for this. So 2x is not equal to minus 3. Bring it this side. Or x is not equal to minus 3 over 2. So for this function, what is the domain? For this function, the domain is equal to x belongs to real numbers where x is not equal to minus 3 over 2. I hope you get the concept, okay? Now we will do some combination of our functions with radicals, square roots and squares, and it's for you to give me the answer. If I have y equals to 1 over x square plus 4, Now, what do you think is the domain of this function? X square plus 4. Now we'll see, can the denominator be 0? We'll say x square plus 4 should not be equal to 0. That means x square should not be equal to minus 4, or x is not equal to plus minus or minus 4. Well, minus 4 inside a square root is not defined. So that means what? That means that the function is always positive and there are no restrictions on this functions. Okay, so you may have something in the denominator, but still the function may be continuous. Here the domain is x belongs to real numbers. Okay, very important to understand. If you graph it, if you graph this particular function, then what should you expect? Well, all the values are positive, right? And it is always continuous. Well, if you graph it, you may get a value like this. Okay, at 0, when you put in 0, this value will be 1 over 4. So that point will be 1 over 4. Okay, you can write the range. Range is between 0 and 1 over 4, including 1 over 4, but not including 0. Okay, be careful when you write this range. Okay, now let me give you one more example of a combination of reciprocal function and our polynomials, right? Now in this case, there are restrictions. Y equals to, let's say, 1 over x times x plus 1 times x minus 2. Now here, what are the restrictions? The denominator cannot be 0. That means the restrictions are that x is not equal to 0, is not equal to minus 1, and not equal to plus 2. All the three values, if you put them here, any one of them will make the function 0. Therefore here the domain can be written as x belongs to real numbers, where x is not equal to minus 1, 0 and 2. So it's good to write them in order. Even if you don't maintain this order, it is okay, but it's not real, it doesn't look nice. So better put it in particular order. How about this function? Y equals to square root of x square. Instead of plus, I'm now making it minus 4. Now if you solve the same equation, we get x square minus 4 should not be equal to 0. That means x square should not be equal to 4 and x should not be equal to plus minus 2. Correct? So in this particular case, the domain is x belongs to real numbers, where x is not equal to plus and minus 2. Right? Like this, you can have many examples. And let me put a square root in the denominator this time. And let me also write, instead of y, fx, because all these are functions. And I could have written fx for all the previous equations also. Okay. Now, let's say we write it like this, equals to 2x plus 1. Now in this case, the denominator should not be 0 and should not be negative also, because then the square root will not work. Therefore, we will solve the inequality 2x plus 1 greater than 0, not greater than equal to, greater than 0. It has to be positive, greater than 0. When you solve it, you get 2x is greater than minus 1, or x is greater than minus half. And therefore, what should be the domain of this function? The domain of this function should be x belongs to real number, of course. And what is the restriction? Restriction is that x is greater than minus half. Okay, so we have taken a couple of examples, and most of the time if you are dealing in equations, these are the examples which form the base for you. Correct? If you understand these examples, then it should be easy for you to write domain of any function given an equation. Review this and see whether you understand or not. If you don't, put some comments on the video and I'll be more than happy to answer your questions. Okay? Enjoy this video, go over it once again and try to get all the concepts. Thanks a lot. Okay?